Beta decay theory, psi, was a revolutionary development in the 1930s. And for the next 40 years, it was used for physicists to understand the beta decay. And everybody was very, very happy about it. But eventually, we know that it is replaced by a deeper theory, which is the electroweak theory. So this four psi Fermi theory is in some sense similar, in my opinion, to the Higgs mechanism.
May I ask, therefore, that you do not believe in fundamental scalar fields? You think it will be replaced?
All I can say is I believe it's not the present understanding of a standard model. It's not the final model. In particular, the symmetry breaking mechanism as phenomenologically proposed by Higgs is not satisfactory.
Okay, thank you.
Now, may I move over to the gravity sector? With the tremendous success of gauge theory applying to the three fundamental interactions, as you have beautifully lectured, now the first frontier of physics, gravity, starting from Galileo, is now becoming the last frontier. And do you have any comment about how one can possibly bring the gravity sector under the same umbrella of gauge theory? And in asking you this, I was also having in mind of your 1974 paper on the gauge theory of gravity for the pure space. Do you have any more comment on that?
It was obvious for many years, since the 1970s, that one needs to understand the relationship between general relativity and gauge theory. And it was addressing such a question that I wrote a paper in 1974. I do not believe that paper is correct. But the problem remains a very important problem. That gauge theory and general relativity are very similar. It's obvious. You look at the equations, they are very similar. And yet, Einstein's philosophy does not follow the gauge principle. So therefore, the true relationship between these two is a fundamental question. And I believe that in fact is related to why we have not succeeded in quantizing gravity. These are different problems, but I believe they are deeply related in a way which requires new brilliant ideas.
Any other question? Yes.
I think we all in this lecture hall can be happy and grateful to be around and following and participating in physics in this historic time when the Higgs boson was finally discovered. Do you hold out hopes that we may also, within years, see the discovery of magnetic monopoles, which I understand are a real prediction of non-abelian gauge theory?
I have no idea. The monopole idea was very, very beautiful, was appreciated from the very beginning. With the identification of the mathematics of magnetic monopoles with non-trivial bundles, I think that the elegance of monopole theory is greatly enhanced. So therefore, if you buy Dirac's idea that what is most beautiful must be used by nature, then you would say there has to be magnetic monopoles. But on the other hand, there has been enormous number of searches for magnetic monopoles, all of which failed. So one cannot argue against that fact. So I do not know how to answer your question.
Yeah. Professor Lee.
But by the way, let me add a thing, because that perhaps is not generally known. I want to make some propaganda for a paper that I wrote with TTU. I think it was in 1975. After Wu and I established the equivalence of the mathematics of gauge theory with the mathematics of fiber bundles, we applied that new concept to rewrite Dirac's paper of the magnetic monopoles. You remember Dirac's paper has a quantization rule, namely Eg over h bar c equal to 1/2 times an integer, where G is the magnetic charge of the magnetic monopole. Now this quantization condition is clearly a quantum mechanical one, because it has h bar in it. So TTU and I asked the question, how about in classical mechanics, in classical electrodynamics? So let us not quantize it. Let us only start with the classical electromagnetism and try to write down classical electrodynamics of a charged particle E and the magnetic monopole G with the electromagnetic field. So we tried to write down that, and that was successful, and that was published in 1975. The net result of that is the classical theory of E, G, and the electromagnetic field is a very elegant theory. However, you find the action integral of this theory cannot be uniquely defined. Like if you do not have the magnetic monopole, classical E with the electromagnetism has a well-known Lagrangian formalism, and that yields an action integral which is well defined. If you now include G in it, then we found that you can still have an action principle, but that action integral can only be defined modulo Eg over C. With that formalism, next you would say, if you apply Feynman's path integral, you remember in Feynman's path integral, you have an exponential of I over h bar times the action. If action is definable only modulo something, then when that is put of the exponent, you would immediately get Einstein's, you would immediately get the Dirac's quantization rule. In other words, Dirac's quantization rule is a combination of Feynman's path integral formalism of dynamics when you have magnetic monopoles. However, we were very happy about that paper of, I think it was 1975. I think it was published in the Physical Review. The next step for Wu and me for the next couple of years was to quantize that, because that was a classical theory. That quantization led to great difficulties. Eventually, Du Dongsheng, T.D. Wu and I together published a paper, I think it was in 1978, in which we claimed we solved the problem through a Hamiltonian formalism. But that was not an elegant thing. I was never satisfied with it. There's new development in this last year. A young theoretical physicist named Wang Zhong in Tsinghua in Beijing solved this problem, and he has published a paper showing how the result for the classical theory of E, G, and the electromagnetic field can be converted through Lagrangian formalism into a consistent theory which gears the direct quantization rule. I recommend that paper to you. I forgot which journal it's published.
Could you please make a comment on the string theory? Is it a way to the fundamentals of physics?
String theory has two aspects. It's a mathematics aspect. It's a physics aspect. I have never worked in string theory, so my opinion is formulated only through conversations with experts. My understanding is that string theory in the last 30 years has made brilliant, unexpected contributions to mathematics. In that, through string theory, mathematical facts were proposed, which were very amazing and surprising to the mathematicians, which, however, having been told about such proposals by the string theorists, mathematicians were able to prove that these statements were in fact correct. So therefore, as far as I know, modern mathematicians greatly respect the contribution of string theories. As far as physics is concerned, string theory is not a theory in the traditional sense in physics. So therefore, it has no impact in physics so far.
Is there any possible apply the conceptual qualities of equation and the theory of interactions to the modern or contemporary philosophy?
The question is that if this conceptual development of this Maxwell equation has any impact in philosophy, can be used in philosophy,
I've never studied philosophy. I cannot answer your question. But if you review what I have told you in the last hour and a half, you will find that what I was emphasizing were the very simple conceptual origin, the conceptual motivation of some fundamental developments in the last 150 years. I believe eventually, hopefully, new, simple conceptual origins, which have not been dreamed up yet, will be dreamed up, and that would lead to the next breakthrough.
Okay.
Find out what you think about the acceleration of the universe. I say, what's that impact on the physics?
Can you repeat your question?
What do you think about the discovery of the acceleration of the universe? Acceleration of universe. Yeah. What's that impact on theory?
Modern astrophysics is making enormous progress, in particular through the work of astrophysics in the last 30 or 40 years. We have now great puzzles. Such things like the dark mass and the dark energy are mysterious. When dark mass was first discussed, I was very skeptical because I thought it was just one type of experiment about the revolutionary period of nebula. But later on, there were many new developments which together show that this concept of the dark mass is has to be correct because there's so many different manifestations. Therefore, it has to be recalled. One has to accept that there is a great experimental puzzle with many manifestations, which does not square with our fundamental laws of physics as we know it today. Then came dark energy, another mystery. I believe that these are very important questions for the next decades. But how they are going to be resolved is poses a question which is of a different nature from what we have been talking about this afternoon. What we have been talking about this afternoon was a satisfactory theory which has some elements which are unsatisfactory from the viewpoint of its elegance and it's too phenomenological, as we said repeatedly. But when you come to dark mass and dark energy, it is a different thing. You are confronting experiments. Whether the resolution of these two different problems are related to each other, I do not know. It's good.
Okay. Last question. what's your advice to the career path of the physics student, especially those who want to study theoretic high energy or particle physics?
I have had a long career in physics. So these days when I give lectures to audiences like today's, I've always been asked the question, what advice I can give to today's graduate students. I do not know how to answer that question because physics today is enormously different from the physics when I was a graduate. The main difference is the following. In many senses, physics was much simpler in those days. You get the impression that if you take 3 or 4 or 5 fundamental courses and work hard on them for 6 months for each course, you sort of understand everything about everything fundamental about physics at that time. Today, it's enormously different. Every branch of physics becomes many sub-branches. Such disciplines like material sciences did not exist. Nanosciences did not exist. In other words, today's what is defined as physics today is very different from what is defined as physics in my student days. Does that mean that it's unfair to today's students? Yes, in some sense. It's much more difficult for a student of physics today to get the feeling that I have taken enough courses. I now know what were the fundamental things in physics today. That is an impossible task today. But on the other hand, you can turn this disadvantage into an advantage, because that means that there are enormously number of directions in which you can make fundamental progress. And so therefore, yes, the environment is different. And the graduate students today must realize that there's this difference and try to make the best of the new opportunities that are being offered to you.
Okay, let's thank our speaker again for a very enlightening and very interesting talk. Thank you.